things off with this example that's in the book. There's a couple different tests that I want to consider for testing this hypothesis right here. I want to consider, this test is in the book, so test 1 is going to be, I'm going to reject if x is equal to 5. So we're just going to see one sample out of this distribution. Very often I set problems like this up on the midterm and final, and people often come up to me and say, do I get repeated samples out of this? How many times do I sample out of it? And I almost always say it doesn't matter, because it just changes the n in there, in the problem. Now I would agree with the Bernoulli, you probably need to sample at least 2 times, you know, for us to get some asymptotics out of it. So if I wrote things down as a Bernoulli with a bunch of n's in there, it would be the same as like a binomial with that being n in the problem. And if I gave you a binomial distribution, maybe binomial 5, so n is equal to 5, so it would be equivalent to a Bernoulli where I repeated the trials 5 times. At least the inference would be identical. The process is a little bit different. If I ended up saying I had m of those binomials, then I would have m times 5 of them. So again, it's like all the math works out exactly the same. So if I ever give you a binomial problem, don't stress out. If I tell you that you get n samples from it, then just multiply whatever this number is by that n. And that will be your effective n, and your n tilde. If I just give you a binomial of 5, it's ready to go. It's got the asymptotics benefit to it. Okay, so test 1, if we want to test that x is equal to 5, this is at least rational that if x is really big, right here, we might be thinking that the probability has to be really big. And this is asking this question if the probability is less than a half, so not overly big. So this seems like this could be a rare event right here if theta was 5. Or if theta was 1/2, x was 5. But it's not impossible. Another test. Say x, we'll say reject if x is equal to 3, 4, or 5. So these are 2 different tests. And this is probably the more sensible test just on the surface, that this is half of the sample space, the other half is 0, 1, and 2. And so that kind of aligns with this hypothesis. So this is probably the rational thing to test on. And you might get something like this out of the Neyman-Pearson Lemma or the likelihood ratio test. So we didn't derive these rejection regions, we're just stating them so we can draw some power curves. And I'm going to say there's going to be a third test we can think about, and I'll leave that test for later. There's all kinds of different possibilities for the data. You probably wouldn't want to say, I would reject if x is 3 or 5, but not 4. That wouldn't make a whole lot of sense, just because of the ordering of everything. And keep in mind, for the likelihood ratio test statistic, it's bounded on one side. So there's kind of an ordering implied in that likelihood ratio test statistic. And so it's probably going to give you data spaces or rejection regions that are ordered a particular way that adhere to that one-sided bound. So we'll talk a little bit more about that on Friday after we go through the Neyman-Pearson Lemma. And I'll say what it doesn't say pertaining to the sharp test. So we'll go into that. I don't think people understand that subtlety right off the bat. That everything Neyman and Pearson said is true mathematically, but maybe it's only reasonable to do when you're testing one-sided hypotheses because of the one-sided nature of the likelihood ratio. So I'll try to make that point a little bit more clear later on. If I wanted to work out the power, so I would say B1, this is going to be the power function. For test 1, so I'll say B1 is a function of theta, that's the probability in the model. So that's whatever your parameters are. That's just going to be the probability x is equal to 5, given theta. So this is the rejection region. So remember that a power function is the probability of being in the rejection region. This right here, prob that X is an element of the rejection region. Given theta. So that's what that always is. That's the power function. So we can work this thing out. It's pretty easy in this case. X is equal to 5. We know what the model is, so that tells us what the probabilities look like. So the probability that X is equal to 5, given this probability theta, is just theta to the 5. So let's just do this one. So test theta 2, theta. This is going to be equal to the probability that X is an element of 3, 4, or 5. Given theta, we just work through these binomial probabilities. So the probability of a 3 is 5 choose 3, theta to the 3, 1 minus theta to the 2, plus 5 choose 4, for 4 successes, theta to the 4, 1 minus theta to the 1, plus theta 5. And if you'd like to write this down, it's 5 choose 5, theta to the 5, 1 minus theta to the 0, so that you can see that formula a little bit more clearly. Go ahead and write it down that way. So these are two different power functions. Let me draw them. So they look like this. These are my powers. Function of theta. Theta is bounded in this case, so I guess I don't need the arrow. So theta is bounded between 0 and 1, and the power is bounded between 0 and 1 as well. So we only have to think about that part of the space, which makes things a little bit easier. Let's draw what this looks like. So this is just a function that's doing this, inclining up. So let me just plug in 1/2 right in here. So this is the null region, and this is the alternative region. So those are the two different parts of the spaces we're concerned with, and I can draw this curve, and it looks something like this. So that's beta 1. And so this is pretty good in here, that if the alternative was true, we'd probably want to reject the null hypothesis. So there's some advantage to doing this, so this probability is really high over here. So we also kind of notice that the probability of rejecting in the alternative space is higher than the probability of rejecting in the null space, and that's a good idea. If the null is true, we don't want to reject the null hypothesis. So we'd want that to be lower over here. So we could work out exactly what that number is right here. So this is the maximum probability of rejecting the null in the null space. So that's the maximum of the power in the null space. Usually we call that the alpha level. Or if you'd already jumped ahead and started reading about Neyman-Pearson, this is also sometimes called the size of the test. So I'm going to use those terms pretty interchangeably, and once we get through Neyman-Pearson, I'll tell you a little bit about more what they're talking about, distinguishing these things. It actually does not matter in the proof that they use to distinguish the size and the level. So the size of the test is what the maximum actually is, and the level of the test is a bounding on that. So basically they want to just show you that if you push the type 1 error down, you push the type 2 error up. So it's the only reason they distinguish that in the proof. And so this number right here is just 1/2 to the 5. And that number is pretty small. So it's like 0.0312. Let me check if I've got that right. Label my graph, 0.0312. I remember that from my coffee this morning. So that's what that is. I can't do that in my head. Nobody in the universe can. Maybe Richard Feynman, but he already passed. So that's pretty low. So the probability of rejecting in the null space. It's capped at 0.0312, so we might think of this as the alpha level in everything. So that's the maximum error I can occur in the null space. So rejecting inappropriately. I might ask the question, if I wanted this to be a half right here, over here, and start thinking about the type 2 errors that I might make. So the type 2 errors are concerned with what happens in the alternative space if I fail to reject. So that's the typical language that we've been indoctrinated with. So, and I can figure out what this is right here, and this would be 1/2 to the 1/5, so I'm just inverse mapping, so that's the 1/5 power, and I'm taking it up 1/2 to spot what this value is right here. I think this number is 0.87. Let me make sure I got that right. Yes. So 0.87. So basically what it says is that the probability of making a type 2 error, or the type 2 error, is only bounded by 1/2 for values of theta that are greater than 0.87. So the type 2 error, because this thing, basically the type 2 error over in this region, over here, is really low. So the type 2 error over in this region is less than 1/2, which isn't great. So we don't make big errors over here, but we are making big errors over here. So I'll just point out to you that 1 minus the probability of a type 2 error in the alternative region, I'll say this, 1 minus power in H1, so this is the alternative region. This is the type 2 error. So the power in the null region is the type 1 error. 1 minus the power in the alternative region is the type 2 error. So, and that's always true. So, and a lot of times you'll just hear people discuss power in the alternative region, and that's where that comes from. So if I wanted my type 2 error to be lower, then I need to do something to this, and I need to consider a different test, and that's what this test 2 is all about. So I can draw this other power curve pertaining to this, and it looks a little bit different. So it's going to be higher over here. Let's see if I can get this to go through the right point. This actually does go through 1/2 right here, and that's because that's half of the sample space, and theta is 1/2, so they kind of pair up. It's the sensible test if you want to balance maybe your error rates. So this curve ends up going up, let's say like this, and then, whoops, no. It goes like this, and then it inflects. It's like that. My artistry isn't very good. It looks like an S through here, and it goes right into this half point, and you can check that. And so now there's a little bit of a balancing in here. So we ended up blowing this thing up, which is bringing down our type 2 errors, because it's the subtraction over on this side. And what is our trade-off to all of this? We had to increase our type 1 error. So, and that's the trade-off to all of this. And so we would be capped at 1/2 on the type 1 error. So again, there's this balancing act. I would say both of these tests are rational, just they're considering different risks in some sense. Let's consider just another test, test 3. I would say reject if x is equal to 0. So this would be pretty ridiculous. So if I set up a test like this, so the power curve, B3, would be 1 minus theta to the 5, and it would look like a reflection of this other curve. So it'd be doing something like this. It should just look like a reflection through that half point. So just based off of symmetry. And what we notice here is the test does exactly the wrong thing. So my probability of rejecting the null hypothesis in the null region is higher than in the alternative region. And we don't want to reject the null when the null is true. And so this is what's called a bias test. So this test is biased. Let me give you the definition of what that means. Test 3 is not in the book for fairly obvious reasons, but we might want to, just instead of having a definition, just one more line on our curve. So a test is unbiased if the power function in the alternative region, so I'll call this theta prime prime, so theta prime prime lives in the alt space. And what we want is this thing to be bigger than what happens in the null space. So I'll say that right there, theta prime is in the null space. So we want the probabilities of rejecting in the alternative space to be greater than the probabilities of rejecting in the null space. For obvious reasons, if you understand it, exactly what we're trying to do with this. We're trying to make the correct decision and not the incorrect decision. If you ever see anybody making the incorrect decision all the time, they're useful. Because don't do what they're doing. So just flip all their decisions for them. In a binary world, that would be easy to play around with, but since there's such a multitude of possibilities, that might not be super useful. Okay, any questions about that? This example minus test 3 is in the book, but I wanted to just take a moment to motivate this definition. So this is a definition. We've got enough time to get Neyman-Pearson on the board. And I can at least tell you what the important part of the proof is. Maybe we can at least finish half of it. Usually things that are complicated, I like to see at least a couple times. So I think we've got enough time for that. Let's make sure I know what this says. I want to get it exactly the way the book wrote it. So, Neyman-Pearson. A lot to digest here. So we're going to let x come from f of x given theta. So I've got some probability model. We're just going to sample one point out of this. And I'm going to assume that x is able to tell us about theta. So I don't mean that, of course, x is able to tell you about theta. We sampled it from its distribution. So I'm going to assume the asymptotics are sufficient enough that I can learn what theta is with one sample from x. So just like in the binomial example. So if I were doing this maybe with xi's from a normal distribution and I wanted to test mu and sigma squared, I can't do that simultaneously with just one data point. So I need to get a couple data points. And I could rephrase the problem that I'm sampling x bar and have a couple sample points in there. So this is just done for simplicity. So we're going to test theta is equal to theta naught versus theta is equal to theta 1. So this is the simple versus simple test. Everything we're going to learn about this test is extendable to the one-sided test. If I just drag theta naught out to the right, and I make theta 1, theta naught minus epsilon, and I drag it out to the left. So, and I can extend everything in this argument to the one-sided test just by using my imagination. If this is true for a theta naught and a theta 1 in the set, then if I march those things over, it's still going to be true what I say. If I march them over again, it's still going to be true. If I march them over again, it's still going to be true. So whatever those points are. So I can extrapolate this idea to the one-sided test. What you cannot do with this is extrapolate this idea exactly to the two-sided test or the sharp test. Those are synonyms. So, and the reason why is that the likelihood ratio is not bounded the same on both sides. So we're going to have to talk about that. So the likelihood ratio test doesn't exactly pertain to this. We have to add a constraint to it for everything to work. And that constraint, I'm going to argue, is a lot of sleight of hand that people need to think a little bit more about. It might have seemed like a good idea. It seems fairly rational. When I took Stat 101, I didn't have any complaints. I didn't know what everybody was arguing about. So it took me until grad school to get there. So now we're here, so hopefully we can start to appreciate it. So for the simple versus simple test, I have no problem with what Neyman-Pearson said. For the one-sided test, I don't have any problem with it either. And even for the sharp test, I don't have a problem with what Neyman-Pearson said. What I have a problem with is the abuse over what he didn't say and how people use it. We'll get into that next week or on Friday. Let's just start carving through this. So I'm going to say there's an if statement in here, and there's a then statement. Start filling this out. So there's going to be two conditions in here, and then there's going to be two things in the then part of everything. So if, and let me denote, I'll say let R denote the rejection region. I'll tell you what the rejection region is. The rejection region, so X is an element of the rejection region if f of x given theta 1 is greater or equal to k times f of x given theta 0. K is going to be positive. Give myself just a little bit more room here. X is not in the rejection region if the complement happens. So I'll just write that down just for clarity. F of x given theta 1 less than k f of x given theta 0. So this is just a rule. So does that rule look familiar? You probably know what I'm leading into, because I think I've mentioned this a couple times. So what does that rule look like? Looks like the likelihood ratio test flipped upside down is essentially what it is. So this looks like this. F of x given theta 1 over f of x given theta 2 is going to be greater or equal to k, where k is positive, right here. Oops, 0. So if I flip this upside down, I might end up bounding it over on the right-hand side, so I flip the bound around. So usually in a likelihood ratio test, what we did is we put the null upstairs and the alternative downstairs. In this form, we put the null, we put the alternative upstairs, I should say. What we actually did for the likelihood ratio test, the denominator was the entire space that contained the NLE. So now I'm breaking these two spaces into different parts. If I had taken the null and divided it by the alternative space, I would have bounded it by something constant and not just something living between 0 and 1. If I put the alternative on top, then I need to flip the bound around. So this really is just the likelihood ratio test in disguise. And I don't think they say that in the book. I totally remember sitting there going, okay, cool. I get math. I can follow it. I don't get it. You know, why were we writing it down this other way if we're just going to treat it this way? And there's a good reason for it. It's just making the proof simpler. So I think it's like, let's just make the proof extra simple, and hopefully we can wrap our minds around this, that we're talking about the same thing. So I wrote it down with the sampling distribution, but it's a function over theta, so now I'm thinking of it as a likelihood function. So what does the sampling ratio look like? It looks just like the likelihood ratio. If I treat it as a function over theta, then it's a likelihood ratio. So same functions that we're plugging in, we're just writing it down with slightly different notation and we're flipping the bound around. Could they have made this all look like a likelihood ratio test? I think so. So why did they not do it that way? I don't know. Maybe they just thought this was simpler, or already had it written down with other notation, and they just decided to do that. So the normal stuff that people do, just to slightly confuse us. Chris?
I'm just wondering about the k is greater than or equal to 0, because if k is between 0 and 1, isn't that like, could the test be biased?
Not in this case. Basically, large values of this right here are going to support the alternative, and small values are going to support the null. So it's all monotone. So as this gets smaller and smaller, this number right here, it means that this thing is getting bigger and bigger. So it's cutting support on the null. And because this thing is getting big, whatever this ratio is, it has more support on the alternative. So I don't think that there's any inflections in there. So no biasness. Actually, this will not lead to a biased test. The way that we're doing it for the simple versus simple leads to a biased test, or an unbiased test. For the one-sided, it leads to an unbiased test. For the two-sided thing, we can have a biased test out of this. So we're going to have to come back and talk about the two-sided thing, but it's not in this example. Okay, so 2, this part's easy. This is just the probability. Write it down using their notation. It's the probability of x in the rejection region given theta is equal to alpha. And they're going to call this the size of the test. So let me just distinguish something for us. So probability x in R given theta is equal to alpha. This is called the size of the test. Oops, I'm going to say the max over theta and the null. I'm going to call that alpha. That's the size of the test. So they also distinguish, and I'm going to kick this right under the rug and circle back to talk about this later. They also talk about the max of theta in the null space, probability of x in the rejection region, theta, so just the power function. If this is going to be bounded by alpha, people will call this the level of the test. Very often people use these terms interchangeably. And for this test, the simple versus simple, when I plug everything in, and I'm talking about the null space, there's only one point. So whatever the bound is alpha. So the level is the size on everything. So we could interchangeably use those two things. What they like to do in this proof is cover another case that if they say, oh, we're going to inflate the type 1 air, then it's going to push down the power and make it, it's actually going to push up the power in the alternative region. So if I push down the type 2 air, it'll push up the power and minimize the type 2 airs in the alternative region. So they're just trying to take care of that bounding. It's basically this trade-off that we saw in this example. So I think I'm just going to keep talking about size of the test, and then I'll patch this up and talk about where they bring in level. So, okay, here's the then. This is what we get out of this. If a test satisfies 1 and 2, the test is uniformly most powerful. UMP. Let me tell you what that means. So a UMP and I'm going to say with power, I'm going to call it BUMP, theta, has the property that BUMP, theta, element of the alternative region. So whatever thetas are in there, I would probably clean up this notation right here and just put the theta in there and then tell you where the thetas live. So hopefully this notation is clear to you. For thetas in the alternative region, this is going to be greater or equal to theta star, theta in the alternative region for any other test. This is any other test. In our example, we saw 3 possible tests for testing the exact same scenario from the same probability distribution. So there's a lot of ways you can form tests. You can form them rationally, irrationally, come up with biased stuff, but that's not what we want to do. So what they're saying is if you follow the likelihood ratio test in the simple versus simple or one-sided case, if you've got the likelihood ratio test and it's calibrated to be size alpha, it's UMP. So it has the highest power in the alternative region, which means it has the lowest type 2 error. So that's what Neyman-Pearson's all about. Fixing the type 1 error and then coming up with a procedure that minimizes the type 2 error. So it's that constraint that you build in to balance out this balancing act between the type 1 and type 2 errors. So what it's saying, if you want a type 1 error rate of maximal being alpha, or in our case, the maximal is the actual number, it's the only place it takes on value is at alpha. This test that adheres to likelihood ratio test will have lower type 2 error rates compared to any other test with a type 1 error rate of alpha. Let me give you a scheme. I think some of you have heard this possible scheme maybe a couple weeks ago. Let's say somebody walks into my office, says I've got some data and I've got a hypothesis. And I say, yeah, keep those to yourself, but tell me more. So they say, I want my type 1 error rate, my maximal value to be 0.06. And the reason they say 0.06 is because they have 6 fingers on their left hand. So it's like Princess Bride. Maybe that was the right hand. So they have 6 fingers on both hands. So they just decide to count a little bit differently. And they've decided that a meaningful threshold should be 0.06 instead of 0.05. Okay, that's not exactly right. They probably wouldn't use that number. Does anybody know why we use 0.05 so much?
Fisher just say, yeah, use this.
Yeah, he did say in Stat Methods for Research Workers, where he first talked about a p-value, he did say 1 in 20 is reasonable. So Fisher did say it, but nobody really argued with that. I have seen a paper written, the case for the 0.04 p-value. Somebody at University of North Carolina, a couple grad students wrote that paper, and they were trying to test whether or not anything was publishable. And they got it. So it was a joke. So these sort of things happen. Somebody tested, I think it was like, I don't know, it was a humanities department, that somebody just ended up coming up with big words, writing a couple page paper of just utter nonsense to see if they could get it published in their field. And it got published, and it doesn't say anything. It's just a bunch of big words. So anyway, be aware of that. Why do people use 0.05? It wasn't just because Fisher said. I have a reason. Does anybody know? We have 5 fingers on our hand. That's why we count in base 10. And so if we had 6 fingers on each hand, we'd be counting at base 12, and that would change all of our thresholds. So people that like fill up their gas tank and round to the nearest penny, I think about all these decisions that get made just because we have 5 fingers on our hand. And we count in base 10, and so it's just easy for us to think about. I think it's totally arbitrary. So anyway, let's say somebody walks into my office and says, my alpha level's 0.06. I like that. And they said, I have a bunch of data. I even know the probability model that it's generated from. That will never, ever happen. So you have to create that for them. And that's what takes all the work, is building a model. So my prediction is that we know F. But I say, yeah, okay, you've got your probability model. You've got data. You've got everything set up. You've got a hypothesis. It seems reasonable. At least you told me. I don't feel like listening today. What do you want your type 1 error rate to be? They say, I want it to be capped at 0.06. So I draw a uniform random number, and I see that it's less than 0.06, and I say reject. So let's say I get a uniform random number, it's 0.04, reject that hypothesis. My type 1 error rate is 0.06. So I'll just tell you this, a p-value, and this is true in general, it might not be the right test statistic to use to give you the uniformly most powerful test, but if you derive that test statistic using Neyman-Pearson, i.e. the likelihood ratio test statistic, you'll get something with minimal type 2 errors. So my test does have the same alpha level as maybe this guy's test, but I don't have this condition. I never looked at the probability model. I never looked at the data. I didn't really care, but I still do have a type 1 error rate of 0.06. So a p-value, regardless of which test statistic that you use, might not be uniformly most powerful. If you use the likelihood ratio test statistic, it will be uniformly most powerful. But I didn't do anything like that, so I have a different type 2 error rate. So this scientist that I said reject that null hypothesis, they said, sweet, I get to publish something, I found something significant. Do you know what their type 2 error rate is? Their type 1 error rate is 0.06. It's 94%. It's the complement of that. So you can work that out. So it's the worst possible test you could come up with. So there's a lot of tests out there. Some are good, and some are bad. So if people are just looking at the p-value and not the power curve, I do think it's just the exact same thing as what I just said. So it turns out the p-value under a null hypothesis is uniformly distributed. That statement's in the book. We'll go through a proof of that as well. So we can go through a full-blown proof and understand what a p-value looks like in the alternative space. But I think in the book, they just proved that under the null space, the p-value is uniformly distributed. So it's akin to, under the null, drawing a uniform. But it does something different in the alternative space, and that's the whole point. So I think if you don't compute power in your papers and you just see if your p-value ducks alpha, I don't think anything. I think that might just be like somebody walking into my office and I just am generating uniforms. So I think that there's more that needs to be done, and that's what Wald said. So Wald comes in and tells everybody how to use Neyman-Pearson appropriately and says you have to draw the power curve. You have to consider a meaningful effect size, the distance from your null hypothesis in which you want to test everything. You have to do all of that stuff before you can conclude anything. And that's what everybody forgot to hear. The only time I ever see that scientists are really sensible about this is when they go, geez, my p-value wasn't small, I didn't reject. Then they do the power analysis and go, well, my power's really low, so I didn't have any ability to reject the null hypothesis. Please give me more money so I can go collect more data. And if they do that for infinity, they're guaranteed to reject something. So sweet. Again, not science. So we'll talk more about that. So a test that satisfies 1 and 2 is uniformly most powerful. And the last part is a uniqueness condition. So if a test exists that satisfies one and 2, dot, 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 then all tests that are uniformly most powerful have to satisfy this. size alpha one and two. So what this says is that if you satisfy this condition in your size alpha, your UMP. That's this part. And it also says all UMP tests satisfy this condition. So this is an if and only if statement, is what they're building in here. So it's a uniqueness thing. There is a test out there that satisfies this. It could have been derived through the likelihood ratio test. I want to just bring your attention to the most important part of this proof. It's understanding this equation. So this is the equation we're going to keep coming back to over and over again. So this is what I'll call the master equation. Or I'll say inequality. So let me just give us some notation. I'm going to say delta x is either 1 or 0, and this is if f of x given theta 1 is greater or equal to k, f of x given theta 0. And this is otherwise. This is this other condition when I flip this thing. So this test is just an indicator, and it tells me when this bound is satisfied. So this test adheres to the likelihood ratio test. So this is an indicator on the likelihood ratio test. It just tells me when that's satisfied. We're going to let delta star x be a different test. And I'm going to say both of these are size alpha. I needed to say this right here, that these are both size alpha. I need to have that locked down. What they say in this part is they say level. I'm going to just slide that right under the rug right now and tell you what that's all about later. It's basically just telling me that if you ended up making the type 1 error rate smaller, or I'll say, let's say bigger, we put the cap on it, so make it bigger and bigger and bigger, then we're going to end up making the type 2 error go down lower and lower and lower. So that's the only part that's important there. We already see that in all our examples. So here's the master equation. I'll just leave you with this part, and then we're going to recycle this inequality over and over again and prove these statements. So note delta x minus delta x star times f of x given theta 1 minus k f of x given theta 0, delta star right there. This is bounded by 0. And they just throw this out at you in the book. So they just say this is true. And they don't give this any justification, but this is the part of the proof that they use over and over again. How do you prove this is true? I probably wouldn't start foiling it quite yet, but we will do that eventually. I just check a few different things. This could be a 1. This could be a 1. This could be a 1, or this could be a 0. This could be a 0. That could be a 1, or both could be zeros. So they're both indicators on tests. So this is just some other test. We don't know anything about when this is 1 and 0. It's just some other test. So we already know that when these are both 1s or both 0s, this thing is 0. So that's the equality sign. Let's check to see when this thing is a 1 right here. When this is a 1 and that's a 0, and this is a 1 right here, this thing is positive because of that. So that's positive. So if this was a 0 and that happened to be a 1, this is negative, and this thing is negative. Because that's a 0, so now the bound is going this way. So you just need to check 4 things. Really, you just need to check 2. So, of those conditions. So you just check this, that's true. What we're gonna do over this next is we're gonna integrate over this. And we're gonna get a bunch of power functions. I'll just remind us that when we integrate something like this, when we do the foiling, and I write something like this out, f of x given theta I, dx, this is the power function for theta I. So that's the probability of that. How do we check that? What is this thing? This is the expected value of delta x. So it's the indicator function. So the expected value of an indicator is a probability. So what is that a probability of? It's the probability of the event when this theta value is theta I. So it's just checking that event right there. It's that probability. So those are power functions. So up here, once I integrate over this inequality and I FOIL this thing out, this is going to be 4 different power functions. And we're going to study those power functions and see how they bound each other. And hopefully we can get a bound that says something like the test adhering to this has this property. So that's where we're going with this. Those are the steps. I'll give you back your exams. If you have any questions about this, ask me on Friday after class. So go home, digest everything. If I made a mistake, let me know calmly on Friday and get that all cleared up for you. Aaron? Sarah? Nick? Colby? Honda. Chris. Sam. Go Sam.